Good morning, everybody, and welcome to Physical Science 1. Today is actually the last lecture. Today we'll be covering basically the structure of space and time. We're going to discuss basically the branch of science called cosmology, which is part of astronomy. Cosmology deals with the entire universe basically as just one entity. Obviously, the entire universe has two components in it. It has the observable universe, which is the only thing that we can basically talk about at this point. And then the actual universe, which extends far beyond that, but we can never know about it's the entire extent of the universe. Obviously, at this point, we really don't know what is outside of the universe. We can only speculate. There are all kinds of competing theories about the boundaries of the physical universe, not the observable universe. And what is beyond that? Is it basically an emptiness, like nothing? When I say nothing, we mean by it complete lack of space and time, which is a weird notion to even think about, okay? And or is it maybe another bigger, much bigger universe where our universe is just one of many, many infinite number of universes? This is the so-called multiverse theory. And there are all kinds of other things in there. So at this point, all of these things are basically theories. And since they cannot be tested, it's not science anymore. It's probably more of a metaphysics than physics, okay? So this is the topic of the day. Mr. Einstein came up with a beautiful theory in 1919 that gave us a very good insight. I'm not sharing the screen, Corinne. I'm just talking at this point, just introducing the ideas. Anyway, Mr. Einstein introduced in 1919 a theory called the general theory of relativity, where it gives us a very, very good understanding of the things that are super big, especially things that are supermassive in terms of mass, because gravity at that point behaves in a fashion that is non-classical, and also things that are moving too fast. So this is the general theory of relativity. We're going to explore that. It gave us basically a platform where everything seems to be happening, and that platform is actually a dynamic structure, namely the time-space continuum. I mean, it predicted so many things. One of them is black holes, which now we know exist. Actually, we took a picture of one, M87, in 2017, and gave us also the possibility of gravity waves. So many things, I mean, they came out of that theory. Gravitational lensing, which is also a consequence of general theory of relativity, which was confirmed in a solar eclipse around 1919, where the sun basically was hidden by the moon. And then from there, we were able to see stars on the other side of the sun. And sure enough, the rays that are coming from the star were bent around the sun. And that is actually a proof of gravitational lensing. And gravitational lensing is a very powerful technique trying to understand or study the entire universe and far galaxies and far stars and so on and so forth, far away stars. So this is the stuff that we're going to be talking about in here in terms of the entire class. As I was saying, since this is the last lecture, I will be available for you guys on any time, not necessarily during the Thursday session. So if you guys have any questions, I'll be more than happy to answer them. And if need be, we can go on a one-to-one meeting. Now, if the meeting is for the benefit of everybody, then I will ask you to record it. But if it is just private questions basically related to yourself, then in this case, we will not record them. So this is basically how it works. On Friday, you will have the review for exam 4 open. And let me make sure it's on Friday because I don't want to give you the wrong date on it. It's available, actually, the review for the exam, yeah, the 28th, which is Friday, 10 o'clock in the morning. And the final review will be available on June 4th. Now, the exams for the last exam, exam 4 that is, it's due June 3rd, and the final is June 8th. So that is basically the last things that we have in mind. So hopefully you guys will have the time to go through the reviews. Don't forget that all of the reviews are graded for participation. The fact that you try them, regardless of what you score with them, you're going to get the full credit, and that full credit goes toward your grades for participation. And that is to encourage you to actually prepare for your actual exams. So let me open first of all the file, and let me share with you the screen. Now it should be on, Corin and everybody else. Sounds good? Very good. I don't know. The chat, I can see it. Okay, very good. So, Hubble's law, around 1920s, Mr. Hubble, first of all, there was a story before it. We didn't know that the universe was that big. We thought at that point that the entire universe was a galaxy, and we had an estimate for the size of the galaxy, which was about 100,000 light years across. So that was the extent of the universe as we knew it. We thought that that's it. Messier in the 1900s basically looked at this kind of fuzzy structures in the sky, and he classified them. He gave them classifications. So M in actually M87 is an object, Messier, and he gave it a number 87. So those are basically fuzzy structures in the universe. They turn out to be two kinds. There is actually now the stellar or stars basically together, like for example the Seven Sisters that are popular in the culture. They are actually called the Pleiades. The Pleiades, they are 7 stars when you look at them with the naked eye, but when you look at them with the telescope, they are about what is it? Some several 100,000 stars together. Okay. So that is actually one of the objects that looks kind of fuzzy from a distance. Actually, there is more to it than that. Actually, if you look at the Orion's nebula, for example, Orion's constellation, there is a nebula inside of it, actually, that is several of them, not just one of them, okay? So those are actually globular, cluster of a stars, and those are, they have that structure. But there is another one, other type of them, that was kind of puzzling too, and including one of them is M87, and Andromeda was actually another one that was kind of basically what looks like it's a cloud in the sky, in the night sky, even in the dark sky. And those were basically later on, when Mr. Hubble in the 1920s, he was looking at specific stars that he knows exactly the frequency with which it's emitted. And he knew that because of the work of some women in astronomy who were called, I forgot her name exactly, the leading one of them, were called calculators because they were not admitted to a science of astronomy because they were women. So basically that was the argument then, which is kind of stupid nowadays, but that's how prejudice and bias can sometimes be detrimental to science. Anyway, there was specific classification of actually special type of supernova that we know exactly the frequency with which they emit. Why? Because here is basically the structure that we're talking about. You have a white dwarf star in a binary system with a regular star. The binary, the white dwarf is small enough so that it's not really did not go to supernova. So basically, like the sun, it shrinks and becomes a white dwarf. The sun is not big enough to become a supernova. So this is a small, basically dying, if you wish, star at the end, because the sun is not part of a binary system. So at the end, it's going to go through a white dwarf stage until it runs out of heat, because at that point there is no source of energy. So its temperature starts to cool down until it becomes basically so cold that it's dead. But there are some that are part of a binary system. So what they do in this case, because they are concentrated, they start to feed off of their other partner, the other second partner of the binary. So they start to attract some of the gases, and the gases from the binary star, from the other stars, starts to come to the white dwarf, and the white dwarf starts to increase in size again. As it captures more and more hydrogen, mainly, which is the main component of the stars anyway, it reaches a certain critical mass. And that critical mass is exactly a known value, in which case it's going to go supernova. And it's going to go supernova and shrinks to become even a smaller star, like a neutron star. So this type of supernova, because we know exactly the mass with which it needs to get into that stage, will emit exactly a specific intensity. The intensity is proportional to the amount of mass. So it's going to a specific intensity. So we know with what intensity that star is going to blow. We know exactly the luminance of that star. Since we know that, and there is the inverse square law that can tell me, depending now on its brightness. Brightness is how it looks to me. If you have, for example, two candles, both of them have the same luminance. Both of them have the same, basically, chemistry. Both of them have the same size. Both of them have the same light. If you put them next to one another, you cannot distinguish between them. They are identical twins, if you wish. But if you put one of them at the further away from you, obviously the closer one will appear brighter than the one further away from you, and that is the inverse square law. How bright the closer one depends on the square distance versus how bright they are, because light will spread in a big sphere. And the area of the sphere is 4 pi times the radius squared. So imagine this object is sitting in here and it's emitted a light. So that light is going to spread throughout a big sphere. And so whatever it was, and both of them were the same, whatever it was, it diminishes by the square of that distance versus an object that is closer by, that is going to have the area with which it has traveled is a lot less. And that area is 4 pi r squared still from you, which is why the square law is true. In other words, take two candles, put one next to one, and you're going to see it. Move the other 1 mile away, and you hardly is going to see light coming from it. And if you still see light, move it 3 miles away, and you probably are not going to see it at all, because the light coming from it, it's both the same light, but spread a much, much bigger area that you're going to hardly see in it. Same thing, like, for example, with your signal from your phone. If you're near a tower, you have 5 bars or 4 bars, depending on your signal. As you move away from it, the number of bars starts to drop and drop until at some point you lose all of the bars. That's exactly the point it has to do with this one. So he knew exactly how much frequency there. And there were events that happen in the sky. I'm getting confused between two notions. I'm sorry, I'm getting you. This is one type, okay? This is one way of looking at it. And but there is also another one, the Cepheids, okay? So there are two types of similar in a sense, okay? The phenomenon is similar. Type 2 supernova and the Cepheids, both of them are binary. Both of them are binaries, and both of them emit frequencies that we know exactly what they are. And now, depending on how far we are, depending on how far they are, you're going to determine two things. First of all, the intensity that gives you how far they are, and second, the shift in frequency. And the shift in frequency not tell you not only how far they are, but how fast they are moving away from you. So what Mr. Hubble first of all discovered was that Andromeda, which is one of the Messier objects, was actually a galaxy on its own. His initial estimates for its distance from the sun, our galaxy, was about a million light years from us. Whereas we know the size of the galaxy is only 100,000 light years. So if this one is a million light years from us, that means it's at least 10 times further than the size of the galaxy. So it's outside of the galaxy. Actually, the correct number is 2.5 million light years. So he was off by a few factors, but that's irrelevant. The point being in here is our universe is much, much, much bigger than what we knew. That was a big deal, okay? So that's one thing. The other thing that he discovered also, based on the shift in frequencies, is for the galaxies near us, like for example, especially Andromeda, it looks like it's approaching us, actually, it's coming closer to us. That's why we predict in the future that it's going to collide with our own galaxy. But as you look further away, for the galaxies that are further away, they seem to be moving away from us. In every direction you look. As a matter of fact, they are moving away from each other too. It seems like the entire universe is expanding. And the further the object, the faster it moves away. So that was really the big discovery of Hubble. As a matter of fact, and I mentioned already, Mr. Einstein in 1919, when he came up with his theory, the solution to his theory predicted a universe that collapsed on itself a long time ago, immediately after it was formed. With a fraction of a second after it was formed, because of the gravity, it should have collapsed on itself and the universe should not exist. So in order to fix that, Mr. Einstein basically proposed a constant. He called it the cosmological constant. That is to retain, to keep the universe from collapsing, because he can see the universe is not collapsed. You know the universe is out there. You see the stars. But that cosmological constant was needed because to make the solution make sense. Otherwise, the solution does not make sense to his theory. Obviously, when he heard of the work of Mr. Hubble, actually, he was invited to Hubble's telescope, and he went to Mount Wilson to look at what Mr. Hubble was looking at. He said his famous statement that the cosmological constant is my biggest blunder, basically, in a sense that this is my biggest mistake. I shouldn't really have introduced it because there is no need for it. Now, the universe is expanding on its own, so since it was started expanding, so it's going to continue expanding, and that fixes the solution. So he abandoned his cosmological constant. Down the road, we're going to talk about dark energy, because that's cosmological constant turned out to be actually not a blunder after all. In 1996, which is only a very recent work compared to the early 1920s, we were looking at those type 2 supernovae, and basically what we discovered was the universe was not, because we expected that during the Big Bang, there was a huge explosion that kept the universe expanding and expanding and expanding. But ultimately, because of gravity, we expected the universe to slow down in its expansion. So it's expand initially, like for example, big explosion. But as the parts get further away from one another, gravity will basically slow down this expansion, because gravity attracts everything. So we expected either one of the three scenarios that were possible. Either the gravity is too strong and will ultimately slow down the expansion, and the expansion will reverse actually, so that the entire universe will collapse again on itself in what is probably an oscillation, because the universe could again explode when it's too small, and then it's going to go back and forth like spring. Okay? That was one possibility. The other possibility, if the density of the universe is too low, in a sense that the gravity cannot slow it down, so it's going to expand, and those parts will fly apart so fast that there is not enough gravity to pull it back, then in this case, the universe will continue in expanding forever and ever and ever and ever, until basically every single part of it will fly from every other part in every other direction, basically, and at the end, the expansion is unstoppable. Okay, the temperature will cool down and the universe will never come back to where it was. So that was possibility 2. Possibility 3 actually is a critical expansion, in a sense that there is an exact balance between the explosion, basically, and how fast the expansion is, and the gravity. In a sense, it's a critical value. It's exactly what it needs to be, so that both of them cancel one another. Expansion will continue, slowing down forever and ever, but never completely basically stopping. It's going to reach zero velocity at the end, but it's the same fate basically as the second scenario. Till 1996, all of these scenarios were basically crossed, because we discovered that the universe, not only it's expanding, as we initially have observed in the 1920s, as a matter of fact, it's accelerating in its expansion. So whatever caused it to expand in the first place There is a second stage expansion that happened around 7.5 billion years ago, and it's pushing it faster than what we thought. So it's not slowing down. Forget it. It's not reaching zero velocity at all. Forget it. It's going faster apart. We don't know why that is. We have no clue for it. So we call it dark energy, dark force. We don't know what it is. So that is the essence of dark energy. Again, dark matter is related to another point in here, and the point in here is the following scenario. If you are inside your bathtub and have a rubber ducky, and the rubber ducky, if it's near and you remove the plug, let's fill the bathtub full of water, and then remove the plug, and put the rubber ducky very close from where the water is going in, from the sink, basically, where the water is sinking. You will notice that the rubber ducky will spin fast. But if it is far away from it, it's going to go over a big circle and it's going to move slower. As a matter of fact, you can see it through the Kepler's laws of motion. Planets that are very close from the sun will go very fast. The year on Mercury, for example, is a lot less the year on Earth. The year on Venus is about 2/3 that of the year in here, about 8 months, basically, it goes around once around the sun. The year on Earth is almost half a year on Mars, and so on and so forth. 12 years on Jupiter is 12 years on Earth is equivalent of 1 year on Jupiter. Because Jupiter takes about 12 years to go once around the sun, whereas the Earth would have gone 12 times, basically, in the same cycle. So that is what the point is we're expecting. If we look at the galaxy, our own galaxy, for example, or any other galaxy, the stars that are near the center of the galaxy, where most of the matter is, where the supermassive black hole is, expected to move faster than the stars that are far away around the edge. Like, for example, our sun is about 2/3 of the way from the center of the galaxy. So we expect the sun to move a lot slower than the stars that are very close from the center of the galaxy. If you move further away, for the stars that are at the edge of the galaxy, they should move the slowest. If you find the star outside of the galaxy, that star outside of the galaxy should move extremely slow, and so on and so forth. Vera Rubin, who was a woman, actually, astronomist, I should say, she did that. That's all her job was. She wanted to see if this hypothesis is true for the stars. Because this is what we know from mechanics. This is what big men in Newton, the biggest of them all, has basically predicted and calculated, and this is basically what Kepler has observed and Mr. Newton confirmed, and this does not contradict the theory of relativity, and everything is beautiful up to that point. Everybody agrees with it. The biggest men in physics agree on this thing. There is no argument about it. And here is a woman trying to do the same thing to confirm what other people have observed, and she came up with a different number according to her measurements, according to her observations. The stars further away from the center of the galaxy are not moving slower. As a matter of fact, they're moving with the same speed as everybody else. So there's a problem in here. We expected the more massive objects, the more massive center, to cause this object to move faster and have very little effect on the object further away from it because of the Coulomb, basically because of gravitational force, also inversely proportional to distance squared. Yet in this case, there is a big problem. She recounted in her story basically that she hesitated a lot because she is a woman and she does not really think that nobody will take her seriously going after this big names in physics. So it was really challenged. Look at, again, the bias, the problems with the science in general. Of course, when she basically first introduced her work, a lot of people did not, wait a minute, why are you talking nonsense? That doesn't make sense at all. So they rejected it and they checked it and they checked it again. And basically at that point, it was a confirmation of something that was suspected because of other phenomenon. And there is matter that is in the galaxy. Every galaxy, for most galaxies, okay, some galaxies, they're poor in it. Some galaxies, they're much richer than it. Some galaxies are actually have more of dark matter than than regular matter. And because we call it dark, because we cannot see it, it does not interact with electromagnetic radiation, does not interact with light. We can, if this room, as a matter of fact, that I am sitting in right now, is for the most part dark matter. As a matter of fact, you are sitting in it right now. I mean, if you were to interact with dark matter, you cannot move because of the huge amount where you are sitting right now. Yet you move your hand left and right, and you don't feel it. The reason why you don't feel it, because it's not made up of ordinary electrons, mainly, or protons or neutrons. The only reason why you can grab your hand or sit on a chair without falling through it is because the chair and you and your hands are made up of these materials. And there is the electrostatic interaction, namely Coulomb's force, that causes your hand not to go through it. If this part of the hand, for example, is made up of dark matter, my hand would go through it without even feeling its presence at all. I cannot even see it because it would not be reflecting electromagnetic radiation. So I wouldn't know that it's there. That's exactly what's going on. You and I right now, we are sitting in huge amount of matter. Yet we don't see it, we don't smell it, we walk through it, and it's probably going through us as well, but we don't interact with it. It interacts with gravity though, because it impacts the motion of objects on a big scale. That's the only way it interacts. But we don't, it does not do nuclear force, it does not do electromagnetic force, it does not do the weak nuclear force, so it does not have any of the other properties that we can test in the laboratory for. Whether taking a picture of it, or looking at it, or doing spectroscopic analysis for it, or touching it, or doing anything through it. Run any physical matter through it. We expect, for example, if you swim, for example, or throw a rock, for example, through the water will slow down the rock. So we expect that if I throw a rock, for example, in dark matter, probably it's going to slow down. So if I pick up how fast the rock is losing speed, then I can tell the density, at least, of that thing. And its viscosity, its physical properties. But I can't, because it does not interact with it. It goes through it much like hot knife on butter, basically. And even the knife will experience the resistance from butter. So that is dark matter. So that is actually the reason why we call them dark, both, is because we don't know what they are. We have no idea. It's not because they have this color or anything like that. It's because we don't know. That is basically the whole thing. So this is the entire chapter in a nutshell. So this is everything in this chapter. So until the 1920s, many people believed that the Milky Way galaxy made up the entire universe. So imagine yourself thinking that you live in a and actually this is to some extent it happened to me. I met somebody who got that too, that you live in a town, and that town is actually the entire universe, okay? The entire basically world. And all of a sudden, you hear of different towns, different countries, different cultures, different continents, as if now the entire perspective for your picture has changed. Because of the sheer size of things, unfortunately, we cannot visit the other towns and the other basically continents and the other cultures. That's the only problem with it. Andromeda is about 2.5 million years from us. But there is no way. As a matter of fact, the next star we couldn't reach it, so let alone the other galaxies. But the point being, the universe is much, much bigger, and this is due to this guy. Okay. So he was able to deduce the distance, and here, as I said before, he took several pictures actually, and he found those Cepheids, and they gave him the estimate of the distance. The brightness of light is inverse square law, and I mentioned the analogy with a light bulb, basically, or with a candle. That's exactly the point being in here. So all of these analogies. Then he used the Doppler effect, and the Doppler effect is basically an effect that you're familiar with. If you're standing, even with closed with basically, if you fold your eyes, you close your eyes, you cannot see anything. Just from hearing the sound, you can tell the emergency vehicle if it's approaching or receding. You don't have to look at it. You don't have to see it. You can tell. And that is by the frequency and the pitch of the sound. Is the pitch getting higher and higher in tone, or is it getting lower and lower in tone? Okay. So a higher pitch will indicate, in this case, that it's approaching to you. A lower pitch will indicate that it's moving away from you. Same thing. When Mr. Hubble looked at the frequencies, for example, if you take the hydrogen, which is the main component in the universe, which is, we're lucky in a sense for it. Hydrogen has specific spectrum. It emits specific red. It emits specific bluish color. Okay, and there is actually another color in there in spectrum, about 4 lines in the spectrum of hydrogen. You repeat this observation time and time again, and you will see does not change. So hydrogen has this property. Since the hydrogen everywhere is the same, we expect the hydrogen as it's emitted from anywhere else is going to have those same frequencies. Now you take a galaxy far away, and you look for those 4 lines. Those are the visible lines there. Actually, it has other frequencies there in the different frequencies that we can see. And if the frequencies, they're supposed to be here, and they are shifted this way. If they are shifted towards the red, that is the equivalent of a low pitch. That means the star is, or the source is moving away from us. If they're shifted towards the blue, then in this case, you know. The entire 4 lines, not one of them, okay? And they don't appear red, the blue. They appear shifted towards it. They appear closer to this side. That's what that means. So the red shift and the blue shift are actually, the entire 4 lines move closer this way. Doesn't mean that so they keep their distances more or less and things like that. Their separations, I should say. So the point being in here is that when he looked at them, he found that for the most part, especially the further away object, they are shifted toward the red, indicating that they are moving away from us. Not only that, but he found a law. And that law, basically, that here is the law, basically. The distance is in parsec, and the parsec is basically, what is it, 2 point something or a few light years, okay? Because the distances are huge. So this is per second because the objects are far away from us. And this is how fast they move. Okay, how fast they move. This is the velocity, and this is how far they are. As you can clearly see, it's more or less a line. Some of them are moving faster than others, but they are moving further away anyway. And this is the 0 velocity. Others are negative. The closer by objects are negative, meaning that they're actually blue shifted. So the ones below the line are actually blue shifted. Everybody else is red shifted. Everybody else is moving away from us. Okay, especially the very close object. These objects are very close by. This is where Andromeda is. This is where Triangulum is. This is the stars in our local group. I mean, stars, galaxies in our local group. So these are the galaxies that are nearby. The galaxies that are further away, they're receding from us, and they're moving with tremendous velocities at some point. And the further they are, the faster they move. As a matter of fact, he expressed this law into this expression. V equal to h naught times d, where d is the distance and v is the velocity. H naught is a constant. H naught is just the ratio of the slope in here of this graph, that's all. So H naught is constant, known as the Hubble constant. Okay, so that is really what's going on in here. So the universe is expanding and expanding very fast. The further away the objects, the faster they move. As a matter of fact, some of the objects that are very, very far, around 13.7 billion light years from us, they are moving faster than the speed of light. And it's not because they are moving, actually. There is the analogy is not that the objects are moving. Nobody is moving. The galaxies are not moving. What is happening in here, the space between them is expanding. Because I said something and somebody might object on it, and that is, how could these galaxies move faster than the speed of light? Because the galaxies are not actually moving. The galaxies are actually in their position from the day when they were basically born. It's the space between them that is expanding. And the space is immaterial. It does not have a mass. So there is no reason for it not to exceed the speed of light. It's not constrained to the same laws of physics that we know of. So it itself is really a weird concept. But this is the point. That means that objects that are right now 13.7 billion light years from here, and they sent their last light to us, they will immediately fall into the outside of the observable universe. So the stars, the galaxies that we're looking at them right now, 13.7 billion years away from us. That is when they send their light. So right now, they are not actually there at all. They are further away that we cannot go, that we cannot see them actually. So what you are seeing, we're seeing them 13.7 billion light years ago. Same thing, Andromeda, when we look at it today, we're looking at it how it was 2.5 million years ago, not today. Today, it might look completely different. For all we care, it could have been disappeared completely. It could have disappeared completely, or something weird happened to it. But we wouldn't know until 2.5 million years in the future what happened to it today. So when we look in the sky, what we're actually looking at, we're looking at things how they were in the past. Even the sun, when we look at the sun today, right now, if you look outside in the sun is not what it is right now. That was 8 minutes ago, how the sun looked, because it takes about 8 minutes for the light to reach us from the sun. So when you see it now, when you go and look at it now, it's actually 8 minutes ago. You have to wait another 8 minutes to know how it is right now. So if the sun, for example, goes, let's say, for example, black hole, which is not, or white dwarf, for example, shrinks completely right now. We wouldn't know. We'll have to wait 8 minutes before the light will go out, before the darkness happen. So at least for 8 minutes, we're good. Same thing for any star, for example, Proxima Centauri or the other Centauris. If you look at them, they're about 4 years ago how they looked like, but not today. You'll have to wait 4 years in the future to know what happened to them. The point I'm trying to say in here is this object, especially the further away, they are outside of our observable universe right now. Actually, they are completely out. So if you try to go to them, even with the speed of light, you will never reach them. They are completely fallen to the other side where we cannot reach them. And that is the problem with the expansion. So what's going on now is that this is the theory that basically that we have. The universe started about 13.7 billion years ago, because this is the hypothesis for the Big Bang, basically. If you take everything, since we know things are moving away from each other, if you play the movie backward, basically, you will find that 13.7 billion years ago, everything must have been into a single point called the singularity. For some reason, things started to expand and expand rapidly from there. So there was a time, an initial time, where the entire universe went through an expansion. First of all, there was a Big Bang. There was some quantum fluctuations immediately, and that is when the forces start to break down and all of these things between them, from the one force into four forces and things like that. Then after that, the universe went through a huge, tremendous expansion to almost its current size. And matter starts to basically develop from there. But 380,000 years immediately after the Big Bang, when the temperature cooled down enough for light to escape. During the initial stage, the temperature was, the density was so high, and that nothing could escape, including light itself. Then after that, light escaped. And that is basically the cosmic background that we were able to take pictures of. This is one of the proofs for the Big Bang. So why we think that this is true, okay? There are other proofs for it. So based on this model, we should expect to find this cosmic background radiation. We should be able to see it, okay? Cosmic microwave background radiation. So we should be able to measure it. And sure enough, we were able to measure it based on how the models predicted the structure. So it looks like we're on the right track. So this theory is on sound footage. there is a proof for it. At least one of them is this cosmic background, microwave background that we were able to measure. Okay, so this is for 13.7 billion years, the universe is expanding. There is actually a tilt in here, and we're going to come back to this graph later on. There is a tilt, and that is happened about 7.5 billion years ago, and that is the second expansion that we're going through it. So we're actually going through a second Big Bang. So there was an initial one that formed the universe, but for some reason the universe went through another one from the initial expansion from 13.7 to about 7.5 billion years. It was expanding. It probably was going to slow down or do something to it, but for some reason 7.5 billion years ago, that expansion accelerated for some reason. So we're going through a second one right now. So how do we know that the Big Bang is correct? Well, continuing expansion of the universe. So that is one thing. Play the movie backward, and you should be able to easily imagine that there is a starting point where everything was in the same point. Then the measured cosmic background radiation also predicted by the theory, it was measured, and it was measured with a tremendous accuracy. So that is actually another proof for it. And then also the models for the Big Bang predicted the dominance, because the time 380,000 years was not enough to form any other heavy materials, because the matter was too dense at that time. So the models predicted only the initial basically element, which is hydrogen, and maybe helium, with a proportion of 75% being hydrogen and 25% being helium. This is exactly the proportions that you see almost with every spectral analysis for every single star out there. The proportions are very close from it. So that is a confirmation actually of also the Big Bang. So it's not a theory. I mean, when we say theory, and I met this guy actually who was, I don't know what his background is. Oh, I don't believe in the Big Bang. I asked him, why is that? He told me, because it's a theory. Well, it's not, it doesn't mean it's an opinion. I mean, when you ask somebody, give me what do you think about so-and-so, tells you I have a theory. And when they say that in the common language, they really mean I have an opinion or I have an interpretation. But that's not how science works. A theory is, yes, based on a hypothesis, but that hypothesis has a huge body of evidence to support it. So it's really more of a collective knowledge, and it's far stronger than what we use it in terms of everyday thing. So there is a lot of evidence for this thing. So it's not in the everyday sense. So it's really on solid observations, basically. So it's not really So here are the two guys who by accident discovered this background noise called the CMB, Cosmic Microwave Background Noise. They were preparing this telescope. Okay, they work at the AT&T Bell Labs, and they found they wanted to tune it, basically the antennas. They wanted to tune the antennas, and they found that some nagging signal was at the end. Okay, was remnant in there, no matter which way they oriented. So initially they thought, okay, maybe it's if we move it away from the city, move it toward the countryside where there is no noise coming from there, we can get rid of that noise. And it's the same background noise that they were detecting in their signal. So they thought maybe, okay, maybe it's the birds that nested in the antenna and with their droppings and everything caused this background noise. So they went in there and they cleaned it and did all of these things in here to it. And they were actually after something else completely. They were not actually after this cosmic background radiation. So what happened was, no matter what they did, they found that CMB in the signal, that noise in there. With an old TV, if you put it with no station, you're going to see those fuzzy things that go around every which way. That is actually the cosmic background, the cosmic microwave background noise that was discovered. And they were actually, they won the Nobel Prize, both Penzias and Wilson, for it. The point being in here is that this is an experimental proof for the theory. Okay. And also, furthermore, the mapping of the entire universe based on the theory matches that. So there are places where there is concentration of matter, and there are places of depletion of matter, and this is distributed uniformly in the universe, indicating that whatever caused the actual universe today and the distribution of matter in it must have started from a single point where they shared all of their behaviors in that. This fluctuations, it's a random due to the variations that are basically quantum effects, okay? So this could explain that beautifully, okay? And then also the elements, they did not have enough time to fuse heavier elements, so the only two elements that should exist are hydrogen with the main part and then a little bit of helium. And that's exactly what happened, what we see in here. So that is basically confirmation again for it. So here is again the evidence for it. The Hubble's discovery of the expansion of the universe, indicating that you can play the movie backward and basically be back into where the whole thing was a singularity, was a point. The cosmic microwave background, that's also proof for it. And that is actually the explosion itself, because that explosion must reverberate everywhere in the universe, and this one exists everywhere. It's like, for example, this is actually the actual Big Bang. So what you see now, that initial tremendous explosion that must have created tremendous frequency, tremendous temperature, that wavelength, which was very short, and because it expanded throughout the entire universe, and it was stretched further and further, so it was very small, and now it was stretched over 13.7 billion years, its wavelength must fall in the microwave region. And that's exactly what it is. So the wavelength has expanded also accordingly. So it went from an extremely high frequency gamma rays, that is the initial explosion, and you find how long now it's going to stretch from that time until now, and you will find it sitting in the microwave, and it's exactly what it is. So that is a proof of the model. So this is really a, and then the relative abundance of the elements, namely that it's still mainly hydrogen and helium because there was no time for it. Now, the other elements, the heavier elements, now they are made in the stars, and that is another story. But the point being in here, at least there must have been a violent explosion that did not let, not an explosion, super fast expansion more than explosion, that did not give time for the other elements to form when the matter was so dense that the other elements will fuse and form heavier elements. So that is actually the third proof for it. So whichever you look, whichever star you look at, you will find the proportions that are exactly coming from a Big Bang and nothing else. Mr. Einstein's theory of relativity came in, actually it was published in 1915. The proof for it came in 1918, 19. The point being in here is that the space and time is only one thing, okay? And the initial theory so basically, it tests, first of all, one of the principle on it is that there is no distinction between a gravity and an accelerated reference frame. This is an unaccelerated reference frame, meaning that you're sitting in empty space. So in this case, you will not feel gravity. Your weight is zero. If you accelerate this spaceship, the person sitting in here doesn't know that the ship has been accelerated, but he or she will feel a force pulling him toward the bottom in here. We call it gravity. But it could very well be the ship is accelerated upward. The same thing. You're going to find the same measurements in here for the weight. So whether you are in an accelerated reference frame or you are in a gravity, you should feel the same thing. So if you let go of these two masses, what happened in this case, the ship will accelerate toward them. But for you, you don't know that the ship is accelerating. So what you say in this case, there is a force pulling them down, because for you and the entire ship is moving upward. And actually what you say in this case, I feel my own weight. So they must have weights also, and that weight is the one that is pulling them down. So this is the principle for the general relativity. So again, local observation made in an accelerated frame of rest cannot be distinguished from observations made in gravitational field. Here is another experiment that we know. If you take a rock and you throw it, it goes through a projectile and falls. That is what we see on gravity. But it could very well be not falling at all, not I mean, following a straight path. So the rock that it comes in here is actually going through a straight line. So what's going on in here, the rocket itself is moving upward and give you that impression that it's going through a parabola, which you yourself, because when sitting on this ship, you think that there is a force pulling you down. So that force must be the same force pulling down this projectile and give you this parabolic shape. But if you look at it from the vantage point of an accelerated reference frame, the rock is not actually under any force. The rock is just straight through, according to first law of Newton. Whereas you feel that that what you call gravity is because of the fact that the reference frame is actually accelerated. Okay, so these are two views, and both views can be interpreted either with gravity for you sitting in the reference frame, or for me outside, I can explain it just with an accelerated reference frame. That's all. Okay, again, the deflections they match in here. So this led to the same thing in here, that light actually should be impacted also with supermassive objects. And that is, light will be bent by gravity. And gravity will act as a lens. So in this case, if I'm sitting in here looking at this star, the star I think is coming from this source, because for me, optics is always through straight line. Just like when I look at an image in here, and I think my image is on the other side of the screen, because light appears to be coming from the other side of the screen, but it's actually a reflected light. It's the same thing in here. It's a bent light, appears to be coming in here. This is similar to the refraction, actually, phenomenon. Similar to actually when you take a lens and you look at an object on the other side, and the object looks like it's coming from both sides to it. This is lensing, actually. And this is gravitational lensing. In 1919, actually, is when the gravitational lensing due to a solar eclipse that was actually observed during daytime. Okay. Time seems to be also affected in a similar fashion. Time actually slows down under tremendous amount of gravity. The clocks on the surface of the Earth should appear to be moving slower than the clocks further away from it. This affects actually the GPS system. The GPS system is actually impacted by it, because GPS system usually the satellites are moving far away from there, and they measure with precision the time in here, so that they have to stay always in a synchronous orbit, and their velocities are high, number one. Number two, actually their gravity is very weak compared to objects on the Earth. Again, I mentioned dark matter. So what we think of ordinary matter is protons, neutrons, electrons that form the atoms and combine to make people and planets and everybody else. Ordinary matter is composed of elements listed in the periodic table. Those are the 92 elements that are in the periodic table. Okay. Dark matter, we cannot walk through it because it's not made up of the same stuff that we're made up of. If matter does not exert the force, then we cannot interact with it. This is invisible matter. So we call it dark matter. Okay. So again, I talked about this point in here extensively. So the objects that are closer from the sun move faster than the object further away. The same behavior should be expected actually for the galaxy too as a whole. But this is not the case. Objects in galaxies orbit at about the same speed no matter what their distance from the center of the galaxy is. This is what Vera Rubin has seen. And this is basically what this thing looked like. So this is what we see the galaxy is, but there is tremendous halo around it, a huge halo, several times bigger than it, where dark matter exists. And dark matter, for some reason, did not coalesce like regular matter to form clumps of stars and things like that. Dark matter seems to be everywhere with the same amount. Even in empty space, what we think is empty space, there is the same amount of dark matter in it. And as I was saying, there are some galaxies that should not exist because they don't have enough stars for them to keep them together. So that galaxy should have scattered around completely. They don't have enough matter in them to hold them together. Yet there are galaxies also, super low density stars. And why? Because there is tremendous amount of still dark matter that hold them together in terms of gravity. So this is basically what's going on with the dark matter. We don't know what it is, but it's out there, and it's out there with a lot of it. Same thing where you are sitting right now. if you could see it, you would not be able to see past your probably your nose because of the fact that there is tremendous amount of it. You cannot actually walk through it if you're going to be able to see it, because then it's going to be everywhere. You cannot actually move your hand because it's too much of it. That's really what's going on. Though in a sense, it's a blessing not to have it interact to the EM waves, because if it does, then we have a problem, big time. Okay. So this is, I mentioned it in how the clumps of matter get together for regular matter, but not for dark matter. And dark matter is basically causing this regular matter to behave this way. Okay. Dark energy is that, again, when we did the observations, we expected the universe to be slowing down, but it did not. Actually, it's accelerating, and we're going through a second stage acceleration right now. Okay. So since it's accelerating and F equals to ma, so there must be a force causing it to expand. And that seems to be like a negative gravity because it's pushing away things from itself. So we call it dark matter. We have no idea what causes it or where it's coming from. So this is dark energy. Dark energy and dark matter have nothing to do with one another, by the way. Both of them are mysteries, and they are not necessarily related to one another. So we don't know what they are. They are separate problems by themselves. So scientists don't know the answer to that question, but they have given it a name, which is dark energy, similar to dark matter. So again, here is the dark matter expansion that happened in the late stage of the universe, okay? So the universe is actually tilted a little bit because of the second expansion. So there is the Big Bang superimposed with the second stage now. Here is the proportions so that you have an idea. You and I and all of the stars together and everything else that we know and see and talk about and do things about is about 4% in the universe. Everything we see, galaxies, black holes, supermassive black holes, everything, the entire universe, the entire planet, and everybody's living in it, including President Biden and his whatever things in there, we represent about 4%. The universe, and the rest 96% or 95 point something percent, we don't know what it is. 23% of that mystery is dark matter, and 73% of it is dark energy. So think about the room where you are sitting. Maybe there is another classroom going on in another dark universe, dark version of our universe, where there people are probably wondering what happened to the rest 4% of the universe. They know, they probably understand their dark matter, and they may even understand dark energy, which may or may not, but they're wondering about probably the 4%, which they can see or they can't interact with, except they think that their gravity is impacting their things and they're accordingly. Maybe. This is hypothetical, okay? So don't start imagining things, okay? So that's what we know today, okay? So again, what is the fate of the universe? And I already mentioned the fact that it's most likely going to go through a big rip right now. Early on is that a heat death basically is going to collapse on itself, but today we know that's not going to happen. As a matter of fact, the universe is accelerating, and this is with constant dark energy, but we don't know that energy at all. So in either case, the universe is going to continue expanding until basically we run out of expansion. So this is the entire chapter in here. I will, this is it. This is your entire class. Usually when I reach this point, I'm kind of emotional and I'm kind of, I feel like kind of basically like we're going not to meet one another. So I wish you the best of luck in all of your other classes. We still have 2 assignments in this class, so hopefully you guys will take care of them, namely the exams, okay? And there is no discussion from this section again. So take care of the reviews. Again, we don't have a regular class from this point on. I know we still have about 2 or 3 periods where potentially we could meet, but we can't because of, I don't mean to do that, sorry. Okay, the point being in here is that I wish you really the best of luck, okay? And if you guys need anything, I'll be more than happy to help you with it. If you have questions about the class, I will be more than happy to also sit down and talk to you about it. There are some events that are coming very soon. First of all, tomorrow morning, if you have a chance and you can wake up early, around 4:30 in the morning to 5:30 in the morning, there is a lunar eclipse, which has some unique properties, okay? It's gonna be a red lunar eclipse, so enjoy it. If you have binoculars and it's the sky and the sky looks beautiful, you can actually enjoy the day and take pictures. As a matter of fact, I'm waking up very early tomorrow morning myself and hope to be able to take some pictures, okay? That is one thing. In October of this year, between 4 and 5:30 in the morning, just before sun, what is it? Before dawn, around dawn, okay? Sunrise is what, around 5:40 or something like that. So it's before sunrise. Okay, so that is one thing. And the other thing also is in October, NASA is launching the James Webb, which is a huge telescope that is going to replace the Hubble. And we expect tremendous amount of science that is going to come from it because the mirror is much, much larger than the Hubble. And it's going to give us a much better understanding of the universe. Is going to penetrate much further away than what the Hubble did for us in terms of galaxies and also about exoplanets. And hopefully it will collect different light from the exoplanets to see if those exoplanets have the correct chemistry that is suitable for life. So in other words, we will have tremendous amount of knowledge. So look forward to that in October. I don't think that there is a specific date in October right now because it depends on the weather, it depends on when NASA, there is usually a window when they will send these things, okay? But this project was delayed and delayed and delayed, and now with Corona, it was delayed even further. It was supposed to happen in May, but it did not happen in May. So it's happening in October. So if you are around and you hear about something, an event in the STEM Center, where the students are going to go live, please join us so that you can enjoy your time also there and discuss things of this nature. Sounds good? Okay, very good. Very good. Thank you, guys. Thank you very much. Okay, thank you, team. Thank you, Alisa. Okay, I'm going to stop the recording.